There are many applications in the world of finance, risk management, where we come across these extreme values or probably extreme events. Those events which can be categorized as very unlikely to occur, but if they occur, they are really creating they are really very costly to handle. They create a big financial damage, right? Those are the events which get categorized as the extreme events or the extreme values. So logically speaking, they can be classified as low frequency, high severity kind of events. So probably we can talk about a big market crash, stock prices falling drastically, or probably big financial institutions like Lehman Brothers collapse, which does not happen every day. It's a very rare event. Or probably any kind of financial crisis, right, like that of the 2008, which is not a very common stuff. So something like that, or any other big natural catastrophes like tsunamis and big hurricanes, cyclones, etc. All these, if I have to really understand their behaviors, because they are going to create big damage in case they are occurring. So the estimation for these things is a very important aspect. How do I estimate? One, the frequency for them. How do I estimate the severity for them? How do I estimate the total exposure which goes towards each of these events? Right? In general, it's very difficult because, first of all, the past data is very few past data points are present. And that too, because of that reason, I see that whatever the estimate that I am making, it would be an uncertain estimate itself. And that too, if I have to do an estimation, not just within the range, but even beyond the range. Let's say some earthquake has occurred and it has been between some unit X to some unit Y on the Richter scale. Let's say it has done some kind of damage. Now, if the earthquake severe than this comes, what would be the damage? It's very difficult for us to estimate. So, especially if the events have not occurred, or if I am expecting that the event can be more extreme than what has occurred in the past. Let's say a stock market crash, right? Stock price falling. Okay, let's say in a single day, if the stock price falls by 20%, what is going to be impacted? What could be the impact on the overall economy? I can't really visualize because we don't see any such kind of instances where the overall index has collapsed by more than this much percent. If these are the situations, very few data is there, and if at all I want to get into the estimate of those particular points much beyond, it becomes very difficult. And this is where it is purely based on the assumptions that are being made by the analysts and the statisticians. So lack of data is really being replenished by the various assumptions, and these assumptions always are subjected to question, right? So generally what happens in these kind of processes is people choose some distribution, let's say a log normal, or let's say a t, or there could be something else. There could be a Pareto distribution. Some kind of distribution is being selected, and the data is fitted to that, whatever the loss observation that we have seen, the data is fitted to that particular distribution. And in majority of the cases, what will happen is the central values will get fitted quite appropriately, but the extreme values will not get fitted properly, which means for the tails, this kind of mechanism does not work. So, which means whenever I am dealing with the extreme values, I need to have a completely different approach. Right? So, dealing with low frequency, high severity events, I really require a different mechanism because these events are very rare. The data is not much present. I cannot combine these particular values with the regular, because regular ones can fit to any distribution, but these extreme ones may not be fitting in that particular distribution. And this is where the overall concept has come out, called as the extreme value theory. Just like a central limit theorem, which is more and more a base for fitting a majority of the distributions, where the central values really can fit the distribution quite comfortably. Extreme value theory is more targeted towards the extreme observations. So this has come out as a parallel thing to the central limit theorem, which is emerging out as a branch of applied statistics, which is trying to address all these extreme value problems. So it is more and more focused towards the extreme values. So which means compared to the central tendency attitude, you find that these models are completely different. Because every statistic that is based on central tendency, it is governed by the central limit theorem. And the central limit theorem, we are saying that it will not be applicable to the extreme values. So we are going more and more with the extreme value based theorems. So which will talk about what kind of distributions should be fitted to our data, and what is the way we can estimate the parameters from the data for what kind of distribution. So they are more and more different, and it's a completely different study altogether. And in some cases it may so happen that the estimation of these parameters become more and more difficult. So whatever we are trying to understand as an extreme value theory, or understanding the characteristics of the extreme values, we really need to look at it as a different branch of statistics altogether, wherein different distributions will come into picture. As we move along, we will be seeing, we will encounter quite a different set of distributions. We will be talking about a Gumbel distribution. We will be talking about a Freshet distribution. We will be talking about a Weibel distribution, which are all governed by the extreme value theory. So we can get into the understanding of the extreme value theory, which can simplify our process of estimating these extreme values that are encountered very frequently in the fields of risk management, insurance, finance, etc. All right. Now let's try to understand this concept of extreme value theory. Right. So what it simply says is you start with some random variable x, and I assume that this x is independent and identically distributed. But I don't know the distribution from where this x is coming from. Right? I don't know the distribution of x. So it is having, let's say, some distribution function f of x, but I don't know what it is. And if I have to find out the extreme var or some kind of extreme value estimation for this particular distribution, because I don't know the distribution, it becomes very difficult using the traditional mechanism. Now if you see the data, let's say I have collected some observations from some distribution. Let me not mention the distribution. I have just collected a few data points. Right? Let me look at it randomly. I have generated some 200 data points. Assume that they are coming from some distribution. Now I want to look at the extreme var for this particular data. Right? Now this is where we are talking about the extreme value theory. So I am assuming that a sample of some size n, right? What the extreme value theory is bringing out to us is, out of that, from that particular distribution, I have taken a sample size n, and in that I am trying to find out the maximum of that sample. Now let's say this is a sample size 200 that I have taken, randomly I have taken. So that's the reason the numbers are changing. I have taken a sample size of 200. Okay, let's look at the maximums of each of these samples. Right, maximum out of this particular sample, yes, the maximum is 3. Now what I'll do is, this is the maximum that is coming out, and if the sample size is large, here the sample size is almost 200. So what we are saying is, if the sample size is large, whatever the mn, which is the maximum value that I have got, 3.00 is the maximum value that I have got. This is what we are calling as the extreme value. Okay. So now let me copy these values somewhere. Okay. This time I got 4.49 as the extreme value. Then I got 3.94. Then I got 3.28. Then I got again 3.01, then this time 2.8, 3.18. Now you see I am getting different extreme values, right? 5.64 is there, 4.1 is there. I am getting different extreme values getting generated out of this. I am just collecting only the maximums here, nothing else. For each group of data, for each sample, I am typically collecting the maximums out of it. Fair enough? Alright, so here I am not concerned with the other data at all. I am only collecting the maximums from this data. Now let's say, alright. Now these are the various maximums that I have collected. Now what it says is, in a very general condition, we will bring in what is called as a Fisher-Tippett theorem. What this Fisher-Tippett theorem says is, as n is going larger and larger, we have taken an n of 200, but as n goes larger and larger, the distribution of the extreme, now this mn, I am talking about the distribution of this. The distribution of the extremes, it converges to a generalized extreme value distribution. Right? So which means the maximums are going to follow this particular distribution called generalized extreme value distribution, which comes out like, it has 3 parameters. One is the eta, one is the mu, and we have sigma. 3 parameters are there, and this distribution is e to the power of minus 1 plus zeta times x minus mu by sigma, 1 plus zeta times x minus mu by sigma, to the power minus 1 by zeta. This comes if zeta is not equal to 0. And of course, if zeta is equal to 0, so 1 by 0 e power minus, so this is working out. If, see, it is e to the power of 1 plus x to the power 1 by x, right? So it is coming of that form of an expression. So it is coming out as e to the power of minus, if I look at it, zeta tends to 0, 1 plus zeta to the power 1 by zeta. It is e power, right? So that's the reason minus e to the power of x minus mu by sigma. So this comes if zeta is approximating to 0. Now this is what we call as the generalized extreme value distribution. So wherein we are saying that x, it is completely, it has to satisfy the condition. Every random variable has to satisfy the condition 1 plus the one that is there, zeta times x minus mu by sigma. This should be positive. Whatever is there within this entire term should be positive. So this is what is being brought out by the extreme value theory. So what it says is all these maximum, they are going to follow this particular distribution. Now if you see, there are three parameters. One is mu, which is called as the location parameter of the limiting distribution Mn. This is the location parameter of Mn. So it is talking about the central tendency of Mn, which is the maximum value, the central tendency of the maximum value. Similarly, I am also talking about sigma. Sigma is like a scale parameter, which is talking about the dispersion, again, of Mn only. This is not the dispersion of the whole data. This is the dispersion of the extreme values. And the third one is zeta, very much important, which is called as the tail index, and it talks about the shape of the tail or the heaviness of the tail. Because if zeta is greater than 0, we talk about a very heavy tail. If zeta is very less than 0, we talk about very lighter tail. And zeta is equal to 0, we talk about a moderate tail. So zeta is a very important indicator of the tail of the distribution. And one more important point is, whenever we are bringing in zeta to be positive, that distribution we call it as a Fréchet distribution, right? Equal to 0, we call it as a Gumbel distribution, and less than 0, we call it as a Weibull distribution. Now, a few important things about this. Here, as I said, zeta is greater than 0. The tail is very heavy. So, the tail follows actually a power function. So, it increases quite faster. So, the tail is very heavy. Generally, if the underlying data is coming from a T distribution, right? If generally the underlying data is coming from a T or a Pareto kind of distributions, if the parent distribution for the data is a T distribution or a Pareto distribution, I can very well expect the zeta value to be more and more positive. And in case of see, this is very much heavy, which is very much possible in case of financial data. Lots and lots of applications in finance, they are heavy tail. So the Fréchet can quite comfortably be used in the financial world. Then, if I am talking of zeta being equal to 0, I said it's a Gumbel. And here the tail follows kind of exponential pattern. Here the tail follows a power function. Here the tail follows an exponential, which means relatively lighter. And if the underlying distributions are something like normal or log normal kind of distribution, we see that the zeta will be very close to 0. Whereas something much lesser than 0, it becomes a gumball, where the lighter tails come up, but probably very few applications in the world of finance where this Weibull distribution can be used. So generally we get into the freshet and the gumball. Now, using the expression once again, e to the power of minus 1 plus zeta times x minus mu by sigma to the power minus 1 by zeta. Now, if I set mu equal to 0 and sigma equal to 1, this is called as the standard pressure distribution, right? The standardized pressure distribution, which will become e to the power of minus 1 plus x zeta to the power minus 1 by zeta, right? So when these two are equal to 0 and 1, it's simply working out to something like this. And similarly, if I'm looking at in case of gumball, it becomes e to the power of minus e to the power of x, right? So this is the kind comes out with respect to freshet and gumball, which are standardized. And what we generally see is both of them, they are positively skewed kind of distribution, right? I see they are more and more positively skewed, but of course freshet is much more positively skewed. Freshet skewness is much higher. The tail will be much longer because the skewness is much higher. So which means if at all I am looking at very large extreme values of x, and I need a higher probability of generating that extreme values, probably I should consider a pressure distribution per se, right? And if at all I am looking at the quantiles, right? Now that this is the probability of the generalized extreme value, what I can really do is I'll equate it to, let's say, some probability p. Now if I am taking the logarithm, it comes log p equal to minus of 1 plus zeta times x minus mu by sigma to the power minus 1 by zeta, right? Or in the other case, it becomes minus e to the power of minus x minus mu by sigma in case the zeta is 0. Now from here I should be able to find out my x, because it is coming out that log p is minus of 1 plus zeta times x minus mu by sigma to the power minus 1 by zeta. Now from here I should be able to find out my x. So x will come out as mu minus sigma by zeta times 1 minus of minus log p to the power minus zeta. And in the other case it comes out as mu minus of sigma times log minus log p. So I am getting my x. Right, to get the quantiles for any probability, if at all I have to generate the stuff, I can quite comfortably generate, let's say from this I can generate the data from a freshet distribution, or I can generate the data from a gumball distribution also. So very simply to look at, so if I am looking at a gumball, I am looking at, let's say, 5%. Right, let me take simple examples. I want the 5% quantile, 5% quantile for a standardized gumball distribution. right? I require the 5% standardized 5% quantile for a standardized Gumbel distribution. So it becomes 0 minus log of minus log 5%, right? So let me look at some of the numbers. If I am looking at standardized Gumbel, right, the 5% quantile is coming out to how much for a standardized Gumbel? It is minus log minus log minus log p, minus log minus log p. So it is giving me somewhere around minus 1.09, right? The 5%, this is only for the extremes. Tell me, believe me that this is not for the original data, right? I have to understand this. Whatever it is coming, it's only the distribution associated with the extreme values only, right? Similarly, if I'm looking at 95% stuff for a standardized Gumbel, it is coming out to somewhere around 2.97. The same logic, if at all I'm going with freshet, probably in case of freshet, let me take the zeta value, let's say, to be around zero point 0.2, right? If I take the zeta to be 0.2, mu is not existing, minus sigma by zeta, minus sigma by zeta times 1 minus of minus log p, 1 minus of minus log p, my 1 minus of minus log p to the power minus zeta. To the power minus zeta works out to minus 0.98. Now the same logic, if I am dragging towards 95 percentile, it is coming out to 4.05. So the minimum is minus 0.98, but the maximum is 4.05. You could see that the freshet is generating a very extreme value. 95% quantile is around 4.05. Now I increase the zeta, let's say, to 4.03. I get that on the higher side it is 4.79, which means the freshet quantiles, if it goes to 0.5, it is going quite drastic. So the freshet quantiles, they are very sensitive to the tail index zeta. As the tail index zeta is increasing, I could see that the extreme values that are getting generated are going much higher and higher. But if the zeta is coming very close to 0, then probably the Gumbel and the freshet are coming very much closer. If I look at this being 0.02, I could see that the Gumbel and the freshet are coming very closer. So as the tail index is coming very close to 0, I could see that the Gumbel and the freshet are more or less overlapping. So just one point, whatever these numbers that I am talking of, 5% and 95%, they are associated with the extreme loss distribution, not the parent distribution. So that's one important point that I really need to understand. Now from this, if I have to really compute, right, if I have to really compute the value at risk, the simple way for me to look at the value at risk is it comes out as mu n minus sigma n by zeta n times 1 minus of minus n log alpha minus n log alpha to the power minus zeta. And in the other case, it comes out in the Gumbel case, mu n minus sigma n log of minus n log alpha. Now, here alpha is the confidence, var confidence level, which is associated with the threshold, which is associated with Mn. So if I really want to find out the extreme var here, I can very well use this kind of mechanism. So probably in the earlier example itself, let's say I am having a sample of size n, which is 200, right? I want to find out the 99.5% var. Let's say if it has been a Gumbel, the 99.5% var for a standard mu n and sigma n, it is 0 minus 1 times log minus 200 log alpha, which is 0.995. And similarly 99.9s and all I can very well find out. Similarly, in case of freshet, I can very well find out. So it is nothing but I'm just bringing in n, right? If you are looked at the simple values of x, we have brought it as mu minus of sigma by zeta into 1 minus of minus log p to the power minus zeta. Instead of log p, we are calling it as n times log alpha, where n is purely based on, n is nothing but the sample size. So this is what is bringing us the expansion, the computation of the value at risk using either the Gumbel distribution or the pressure distribution, right? And of course the choice depending on zeta, if zeta is very much away from 0, I should use the pressure. If zeta is more or less closer to 0, I should be relying more and more on the Gumbel distribution. So we have to be really making a right choice in terms of the correct distribution. Now, how do we really identify whether I should choose a Gumbel or a pressure? What are the different mechanisms that are available which will help me in choosing the Gumbel versus a pressure? First of all, the first way to look out is if I know the parent distribution. If I know the parent loss distribution, I am confident about it. Then there is a kind of a mapping. To a large extent, if a parent distribution is a T, I can see that it will boil down to a pressure. Or if I look at the parent distribution to be a Pareto, I can still look at it being a pressure. But if I am looking at the parent distribution being a normal or a log normal, I can see that the extreme value would be a kind of a Gumbel. So there is some kind, if the parent distributions are very heavy-tailed distributions, then probably their extreme values will follow something like a pressure. But if the parents are more or less closer to less tailed kind, smaller tailed ones, then probably their extreme values are going to follow a kind of Gumbel distribution. So the extreme value distributions can be to some extent mapped from their parent distributions, or for the tail index zeta, I can do some kind of testing of significance. If it is insignificant, I'll go with Gumbel, otherwise I'll go with pressure. But again, I need to have a mechanism to test it out. And probably the best way is to be on the safer side, go with the pressure, because we have seen that the pressure is more and more conservative. It gives a very higher values of the extremes. So probably it becomes more and more conservative in the approach. So for some safer kind of options, probably I can still rely on the pressure rather than with the Gumbel distribution. And once I know whatever is the distribution, I can very well estimate the parameters using the maximum likelihood approach, right? I have to estimate the three parameters mu, sigma, and zeta. So I can estimate them either using the maximum likelihood approach, wherein for each one I can go ahead with the likelihood or the log likelihood and then simplify, or I could go with some kind of regression kind of methods which are going with ordinary least squares mechanisms, or any other kind of semi-parametric estimation methods also do come into picture. So semi-parametric like hill estimator kind of mechanisms, even they can be used for coming out with the estimation of these extreme value parameters. So any of these approaches, so probably here, if I have generated the data from, okay, now you see this is generated from a t distribution. Now that this data is generated from the t distribution, I can very well see that the maximums are going to follow some kind of a pressure distribution. Okay, one way for me is I can look out, okay, these are the maximums I have sampled out, right? One way is I can fit in the maximum likelihood approach for each one of them. Let's see. Let's try out with the maximum likelihood approach, but it becomes slightly difficult when we do it with, okay, so let's say I want to fit a kind of, let's say here I want to fit in a, a pressure kind of a distribution, right? So which means I will be doing the maximum likelihood for this. So what is my likelihood function here? E to the power of, so probably I am taking the likelihood function of each of them, which is coming out as e to the power of minus, so let me take the parameters first. So mu, sigma, and finally I need even the zeta, right? So I'll use some numbers, probably mu let me start with 0, sigma let me start with 1, and zeta let me start with 0.2. So here I am bringing in e to the power of minus of 1 plus zeta times x minus mu, this is x, minus, okay, this thing I have to fit in, okay, x minus mu by sigma, right? The maximums wise I am looking at 1 minus 1 plus zeta times x minus mu by sigma to the power minus 1 by zeta. Okay, so this is what is coming out as the likelihood function e to the so this is what has come out as the likelihood in this particular case. I can very well take the log likelihood function for this. So this is working out to be the log likelihood. I am doing the summation of the log likelihood. This is working out to the summation, and my intention is to maximize this. I use the solver to maximize this by changing these three and the condition that I would like to set is the condition that I really need to set here is 1 plus, right, in each of the cases 1 plus zeta times x minus mu by sigma should be greater than 0. So here I should talk about 1 plus zeta times x minus mu divided by sigma. This should be positive, right? So what I can very well say is, if this entire thing, right, if this entire thing is greater than 0, I'll say it as 1, otherwise I'll take it as 0. So what I'll do is, okay, the same logic which I have to apply. If it is greater than 0, I'll take it as 1, otherwise I'll take it as 0. Which means I'm also looking at the constraint as the summation of that rule. The summation of that rule should be exactly 200. That's a constraint which I would like to set. Alright, so now let me try out. I want to maximize the summation by changing these values, and at the same time set a condition that the summation should be exactly equal to 200. Now using this, if I'm to solve for it, yes, there is the maximum likelihood approach. Oh, sorry, I have to do this not on the original data. I have to do it on the maximums, right? So this approach, I am not doing it on the original data. I have to do it on the maximums that are collected. So these are the maximum. So what I can do, I can find out the log likelihood for each one of them. Logarithm of 1 plus zeta times whatever is the maximum value minus the mean divided by the sigma. 1 plus zeta times the mean divided by the sigma, whatever is the logarithm, minus to the power minus 1 by zeta. So this becomes the log likelihood function, right? This becomes the log likelihood. I extend this log likelihood across. Now I want the maximized value for this log likelihood, because the summation of the log likelihood is going out to something around this. So I want to maximize this log likelihood function. So I am trying to see where I can maximize this by changing this, and let's say, let me not put any kind of constraint. Okay, there is some. So here it is working out that the zeta, okay, probably a powerful computation process has to come in, because here I need to have a constraint also that it satisfies 1 plus zeta times mn minus mu by sigma. So probably what I also look out for is what I should also look out for is I'll set a constraint which is 1 plus zeta times mn minus mu, which is m minus mu divided by sigma. This should be greater than 0. So in all the cases, this is greater than 0 only. Yeah, if this is greater than 0, then only I'll represent it by 1, else I'll represent it by 0. Now again, this should be an iterative approach which is done as a calculation by various tools, right? So probably what we can work it out is if the zeta is coming very close to 0, that's the reason I can very well look at it more closer to a gumbel, right? So probably if I'm trying to solve this again, I'm trying to change mu, sigma and zeta, wherein I'm even putting a constraint that this should be equal to 23. Now in this, okay, there is some issue that zeta is coming out to be very small. Probably the better way for me to talk about is zeta is coming out to be very small. This is the mu, this is the sigma. Because zeta is coming out to be very small, this is working out to be very much closer to a non-calculable kind of stuff, and which is means in this case I can very well associate a Gumbel distribution. But of course here Excel may not be that powerful in terms of testing all these things, but yes, to whatever extent to understand the concept we are talking about, the different values of zeta could take it to a Fréchet or a Gumbel. So I can use these different kinds of estimation mechanisms to finally arrive at the parameters for the particular distribution, and once I am clear of the parameters, I can very well look at the 5 percentiles, 95 percentile, whatever is the quantile that is required for predicting the extreme value at risk. Alright. Now let's look at one very important extreme value theory and the distribution, wherein I am interested in modeling the distribution of excess losses over a threshold. So excess value or excess losses above some threshold value X. See, if I have to really look at the generalized extreme value theory, was more and more modeling the maximum value or a minimum value of a set of data, right? The distribution regarding the maximum or the minimum value. Whereas the similar kind of a concept, instead of looking at just the maximum or the minimum, I want to see the distribution of the losses which are greater than some threshold value X. Now this is where we use this peaks over threshold approach, and this peaks over threshold approach will lead us to what is called as a generalized Pareto distribution. So just to simplify the scenario, if I am interested in modeling the maxima or the minimum value of a particular distribution, which is again one way of modeling the extreme values itself, I will be relying on generalized extreme value theory. But if my objective is to model the values which are greater than some threshold, the distribution of the values which are greater than some threshold, that is where we are using the peaks over threshold or the traditional pot approach, right? So the simple way I look at it is, think of a random variable X which is an independent and identically distributed. Let's say it is having some kind of a distribution function f of x. Along with that, I need to choose one value of u, which is called as a threshold. Now, the choice of this threshold is completely arbitrary. Some kind of judgment is required in the choice of this. Now, whatever is the u that I have found out, then what we are simply saying is the distribution of the excess losses, the distribution of the losses above the threshold u, all we are saying is it is nothing but the probability that x minus u is less than or equal to x given that x is greater than u, right? And this will come out as f of x plus u minus f of u divided by 1 minus of f of u. So this comes out to be the distribution function for the excess losses above a particular threshold, right? And so the base distribution, the loss distribution of x can be any distribution. But what it says is, if u is getting larger and larger, if the threshold is very, very high, this particular distribution, it gets converging to what is called as a generalized Pareto distribution. And the generalized Pareto distribution comes out as 1 minus of 1 plus zeta x by beta to the power minus 1 by zeta if the zeta is not equal to 0 and it is equal to 1 minus of e to the power of minus x by beta in case the zeta is equal to 0. So this is more or less similar to a large extent with respect to the generalized extreme value theory distribution also, right? If we remember, if we try to recollect the generalized extreme value theory distribution, we said that the maximum of a particular set of data will follow e to the power of minus of 1 plus zeta times x minus mu by sigma times sigma to the power of minus 1 by zeta. If zeta is not equal to 0, e to the power of minus of e to the power of x minus mu by sigma if zeta equal to 0. So to a large extent there is a usage of zeta. So but the only difference is here there are three parameters mu, sigma and zeta, whereas here there are only two parameters zeta and beta, right? Now so which means here we have only a scale parameter beta, no location parameter here, scale parameter beta and a shape parameter zeta. The shape parameter, just like the generalized extreme value, is also called as the tail index, and tail index can be positive, negative or 0. If it is positive, it means a heavy tail. Probably equal to 0 is like a moderate tail, and very much less than 0 is a very light tail. And we know that light tailed distributions, very few applications are there in the world of finance. The world of finance is heavily flooded with heavy tailed kind of distributions, right? And the advantage now with this mechanism, see, probably the x, which is the loss distribution, I said it can be any distribution, right? Probably this is a very important result, right? The underlying loss distribution, it could be normal, it could be log normal, it could be t, whatever it is. It could be any distribution. What it is simply saying is, if I am choosing a reasonable threshold u, the excess always follows a generalized Pareto distribution. So irrespective of whatever is the distribution of the parent, which irrespective of whatever is the distribution of the parent losses, if the threshold is high enough, it is that the generalized Pareto distribution is the natural model for all the excess losses. So which means I have to choose U very reasonably. Once I know what is the threshold U, I am trying to find out the number of observations which are above the threshold, which is NU. Now if U is very high, probably NU will be very low. And only if U is very high, it gets converging to a generalized Pareto distribution. So U has to be set very high so that it converges to a generalized Pareto distribution. But at the same time, if it is very high, probably my data would be very few. NU will be much lesser. The data would be very few, which means my estimation of the parameters zeta and beta will become very difficult. Right? So observations are much lesser. The reliability of the estimates will become much of a challenge, which means the selection of U is a much important aspect in this entire process. And probably once I have the data, I can use either the maximum likelihood estimation approach or any other semi-parametric kind of approaches for the estimation of the parameters zeta and beta. And now that we know the distribution and we understand this, if I really want to go ahead with the computation of value at risk, right? Again, just like the way we have done in case just like the way we have done in case of the generalized extreme value concept. If I have to find out the value at risk here, I can take it as U plus beta by zeta times N by Nu times 1 minus alpha to the power minus zeta minus 1. So where alpha is the significance level. Right, so this is directly coming out. See, probably the best way to understand that is whatever was the expression 1 minus of 1 plus zeta x by beta to the power minus 1 by zeta. This I'll set it equal to some p. Right. So it is directly coming out that from here, if I am setting it out, 1 minus p is coming out to 1 plus zeta x by beta to the power 1 by zeta. Now I can make it as 1 minus p to the power zeta is equal to 1 plus zeta x by beta. And from here I can get zeta x by beta equal to 1 minus p to the power zeta minus 1. So from here it comes out that x is nothing but beta by zeta times 1 minus p to the power zeta minus 1. So this is coming out to be my value of x. Right? Now this is the value which I can very well generate using. So now that I have from here the zeta, I can very well generate using the x values. I can very well generate in case zeta is not equal to 0. And again here this is actually minus 1 by. So this actually becomes minus zeta. So 1 minus p to the power minus zeta minus 1. So this is where we are bringing in the computation of var. If you look at it, beta by zeta time. Now here 1 minus alpha to the power minus zeta minus 1. So which is where probably I am looking at, if I really want to look at the mean, I am looking at the proportion of the observations that are exceeding the threshold. So based on that, I am actually bringing in a factor Nu by n is talking about the proportion of observation that is exceeding the threshold, which means n minus of nu by n will be the proportion of observations that are not exceeding the threshold, right? So if I have to compute the var, it is over and above that threshold. So that's the reason I am adding this mu plus beta by zeta times, here I need to know the proportion which is exceeding the threshold. So that's the reason I am using the multiplier n by nu times 1 minus alpha to the power minus zeta minus 1. So this becomes the computation of var at alpha confidence level. So depending on the numbers that I have, I can very well take up, once I know some beta value, once I know some zeta value, once I know the u which is the threshold, and once I know nu by n which is traditionally the proportion of values which are exceeding the threshold, and I know the alpha which is the confidence level, I can very well compute the var as u plus beta by zeta times n by nu times 1 minus alpha, this entire thing to the power minus zeta minus 1. So this is giving me the value at risk at that particular confidence level. And if I am really looking at the excess shortfall, the excess shortfall is expected shortfall. It is coming out as the value at risk divided by 1 minus zeta plus beta minus zeta u divided by 1 minus zeta. So basically it is nothing but value at risk plus mean excess loss over the value at risk. So this is what is coming out. But this is what is coming out in terms of the expected shortfall. I can directly apply the formula where value at risk by 1 minus zeta plus beta minus zeta u by 1 minus zeta. And we have already worked out that the u should be sufficiently large, but at the same time, if it is too large, it is going to be resulting in a very few number of observations. The parameter estimation becomes very difficult. So in order to really work out what is the appropriate choice, we do what is called as the plotting of the mean excess function to decide what should be the value of u. On a judgmental way, I can go with a plot of mean excess function, wherein for different values, right, we are plotting the mean excess for different u. So I am looking at u and the mean excess. So whatever are the values which are in excess of u, I am trying to find the mean. And what it is said is, wherever this graph is becoming more and more horizontal, this graph wherever it is becoming more and more horizontal, that is the threshold value that we are selecting. And we can estimate this beta and zeta just like using maximum likelihood estimator approach, or any other semi-parametric kind of approaches also, right? Now, just in terms of comparing generalized extreme value theory versus the peaks over threshold theory, we have clearly said this is more targeted towards the modeling of maxima or minima in a particular data, whereas this is trying to model the excess over a threshold. Now here the challenge is determining the threshold is a much a bigger challenge, whereas here first of all, one additional parameter, right? We have three parameters here, whereas here there are only two. So slightly complicated. But the major complication with this model is, see, we are selecting only the maxima and we are saying maxima is a representation of the extreme value. How about if there are two extreme values in the data? Probably there is one maximum value but very small than the maximum, right? Minutely different from the maximum, the second one, it is not getting considered as a part of the model at all. So if there are two or three extreme values in this data set, it is, the generalized extreme value theory is not able to handle them. So that's a big disadvantage. While here it is able to handle, the deciding of U becomes a very challenging aspect, right? So this is one of the prime reasons. In some cases, I would prefer a generalized extreme value approach, whereas in some cases, I would be relying more on peaks over threshold approach. And all these mechanisms which we have looked at till now, they are more and more univariate kind of extreme value understandings. But what we could see is there is a possibility of multivariate also. Now, if there are multivariate extreme values, the tails, how do I really look at the interaction between the tails? The correlation between the tails comes into picture. But let me tell you, or probably let me use the word dependence between the tails rather than the word correlation, because correlation is a pure mathematical concept which is more and more applicable if we are looking at the distribution being more and more normal, if the distributions are more and more based on the central limit theorem. But the extreme values are not based on the central limit theorem. So which means these are not elliptical distributions. So for all the elliptical distributions, probably correlation can very well be used to measure the dependence between them. But the moment we go beyond the elliptical, which means going outside the scope of the traditional log normal kind of distributions, correlation becomes a non-applicable kind of a concept, right? So wherever we are talking about the multivariate extreme value theory, it purely suggests the usage of copula based mechanisms, understanding the dependent structure using the copulas rather than the traditional correlation approach, right? So even the multivariate extreme value theory clearly says that the limiting distribution of the multivariate extreme values will be a member of a family of EV extreme value copulas. So this is where we will rely on the different extreme value copulas. We try to execute them based on that, choose the best possible dimensionality between or dependency between the extreme variables. But of course the problem comes with respect to dimensionality, because if I have to really look at one particular extreme variable which has, let's say, 1 out of 100 chance of occurring, another variable where another 1 out of 100 chance of occurring, if they are independent and if I have to see both of them occurring together, probably the probability will be 1 out of 10,000 occurrences, and our data sets are much smaller, so there is no way I can get occurrences as the dimension becomes more and more. So the parameters become very difficult to estimate. But the point is, these kind of extreme values, they are not independent. They depend purely on their joint distribution. I cannot assume that the extreme events will always be independent. Probably if I am thinking of some kind of tsunami occurring or some kind of earthquake occurring, that earthquake can very well result in a big financial crash as well, or some other disaster, which means all these extreme events are not independent. They have interdependence between them. So the tail dependence, how I model it, what particular extreme value or what particular copula I use for modeling the tail dependence is the most important aspect when I am looking at the multivariate extreme value theory. And we all have to appreciate the disasters or the extreme values are always interrelated. They are not existing independently, or they are not working out in isolation. All right.